Thanks for the introduction, Willow. So my name is Rohan. I'm a fifth-year PhD student at Stanford. I work with Alex Aiken and Fred Kilstead. I'm also a part-time researcher at NVIDIA, where I work with Mike Bauer and Michael Garland. So I'm going to talk today about the system we built called Legate Sparse that is going to hopefully make it easier for you to write sparse computations that run on clusters of GPUs and ML supercomputers. So on a single slide, well, what our system is, we build this set of libraries that basically enable you to scale SciPy sparse programs completely unmodified out to scale of supercomputers. So I have on the left some normal Python code. It's sequential. It looks like it's single-threaded. There's no distribution, communication, annotations in it or whatever. But you replace at the top of your program the SciPy sparse import with Legate Sparse. You replace the NumPy import with cuPyNumeric, a distributed NumPy library we built. And this code, completely unmodified, is going to weak scale out from running on a single GPU, maybe storing a matrix of like 3.5 gigabytes, out to running at 192 GPUs of the Summit supercomputer. Just the code like this. And so this is really cool. There's a bunch of interesting things about this code. One thing I like to emphasize is this composition property kind of between the Legate Sparse code and the cuPyNumeric code, where you can create some distributed data with cuPyNumeric. You can pass it into operators like this matrix vector multiply defined by Legate Sparse, get some distributed data back out, and then pass it into cuPyNumeric with no real cost to that. You actually get composition like you often do on a sequential program. We built some pretty interesting programs in Legate Sparse. I'm not going to spend too much time talking about them. You can talk to me later. But we built things like multi-grid solvers, which are commonly quite difficult to build in languages like NumPy. We built the most interesting one was this simulation of some quantum phenomenon we built. And basically the story is very similar, that you can write some pretty simple-looking NumPy and SciPy code and get code that actually utilizes a ton of GPUs on your big machine. So in this talk, I wanted to talk a little bit about building this library, which is really I think the most relevant component to this community. And so in 2019, Mike Bauer, my collaborator at NVIDIA, built this first version of this distributed NumPy called cuPyNumeric. And this started a big buzz within our group, and especially at NVIDIA. So I came in 2022 to try and start developing a companion sparse library to this distributed dense library. And we built a research prototype in 2023, by 2023, and a lot of it was focused on how do we build this sparse library, where all these kernels come from, and how do we actually enable this composition between this dense component and this sparse component. In 2024, people liked our prototype, so it got picked up by engineering. And actually, by the end of this year, this Legate Sparse has been released as an official product that you can actually download. I'll have some download links at the end of the talk. And we actually got some real customers. So people actually bought DGX machines to run the software, which is pretty cool. Our most interesting customer is a payments processor called NPCI. And what they basically use is they have these big transaction graphs created from looking at all their transactions, where there's an entry in this matrix, two people have sent money between each other. And they do a bunch of big SPGEMs on this to basically walk the transaction graph and try and find money laundering cases. And so, of course, a multi-GPU distributed program is going to go way faster than their CPU code. So they're very happy with that. More beyond Legate Sparse, this work has also extended to building a sort of whole framework of composable libraries, where not just distributed NumPy and SciPy, we also have a bunch of things like distributed data frame processing libraries, tree boosting algorithms, and other machine learning things. And all these libraries have this nice composability property where they can import each other, use data created by each other, and this runtime system underneath them is responsible for making sure these programs run at the scale of a single GPU or all the way up to a larger supercomputer. So the actual technical challenges in this work, there are two main ones. And the first one, which is where I actually spend all my time these days doing work, is how do you structure runtime systems and these libraries to actually enable efficient composition between these libraries and actually achieve scale at the same time without costing you performance. So I'm not going to talk about today. I'm happy to discuss offline at the conference. The part that is most relevant today, and also kind of a unique problem to Legate Sparse, was how do we actually quickly build a library of these distributed sparse operations in a way that they're both high performance and they don't, you don't want to tear your hair out the whole time while writing all this low-level code. So to motivate the problem, and I'm sure this is a slide that many people have seen in many different ways, but so to build something like SciPy, SciPy Sparse, it has a ton of different functions in that library, and of course all of them are defined over many different kinds of matrix formats. So you get this classic combinatorial explosion we've already seen a few times today. where you have a bunch of operations like matrix vector multiplies, matrix multiplies. And then you have a bunch of different formats you want to support that are all important. You have a bunch of backends you want to run the code on, like a single-threaded CPU, a multi-threaded CPU, a GPU. And then also in the distributed layer, you have another sort of addition to this cross product, where you may have multiple distributed algorithms for the same computation that you might want to choose based on the data, based on the structure of that sparse matrix or the context you're using it. And so in our case, we really wanted to get very high performance, so we want specialized kernels. It simply doesn't suffice to write, one CSR SPMD and copy your data in and out of that format every time you want to, you want to do an SPMD. And so on a distributed machine especially, where the costs of moving data between nodes is very expensive, we really want to keep our data where it is as much as we can to make the code run as fast as possible. So to tackle this problem of actually building, all the sparse kernels in our library, we leveraged this work that I did earlier in my PhD called DISTAL. And so DISTAL is a tensor compiler from the Taco family of work that basically you can write. It helps you develop distributed tensor contractions and actually run them on your cluster of machines. So like a lot of the other tensor compilers that we built, it takes in a notion of what you want to compute, something like an Einstein summation notation, just expression like Taco. And it also takes in a notion of how your data is compressed, this level-by-level description of your data formats. The interesting stuff in DISTAL, the new stuff is basically talking about how your computation is distributed, an algorithm that describes how you want to chop up this computation across all your nodes in your machine, as well as a notion of how you want to distribute your data. The way you place your data originally on this machine can differ from how it should move around during that computation. DISTAL takes in all these things and outputs you code that runs on a supercomputer. So I'm going to talk a little bit today about this, how we talk about data distribution, how we talk about computation distribution, and how we actually generate some of that distributed code used in that actually runs on this machine. So to talk about how you express the compiler, how you want to distribute your programs, well, there's just a few additions to a standard scheduling language like Taco that you might have seen. So you have your programs represent these nested loops. You have these Einstein summation notation expressions. And to talk about data distribution of computation, well, the most basic thing is you basically say, hey, I want a particular loop, to be split across and run across all the different GPUs or nodes in my machine. And this transformation basically gives you out one of these loops that has been distributed. The other thing you need to do is control when communication occurs. And we have the way you tell the compiler this is that you say, I want to communicate a particular tensor in my program at a given level of my loop nest. And the basic way that you can imagine how this works is that what this is saying is that at every iteration of I want you to go figure out the data needed of this sparse or dense matrix at this particular loop nest, gather the data for me, and then actually run the computation that runs inside that loop nest. These transformations are sort of very simple. I think they're things you might expect to see if you're writing these programs. But the hard part, really, that is actually generating the code that does what the user is asking for. And there are two main things that make this really tricky for sparse programs, is that one, as we've seen before, these data structures are full of indirections. There are a bunch of arrays with scalars pointing into these other arrays. And then those indirections are also only dynamically known. You only know where these things point when you actually have the data in your sparse matrix. And many times we're not willing to specialize something just to a particular just sparse matrix. So to talk about how we get into this and some of the challenges, I just want to remind everyone about the CSR matrix representation, just so we're all on the same page. So CSR matrix, you have a collection of arrays, usually called pos, CRD, and vals, and the pos array has an entry per row in the matrix, and it basically represents a range of data in the CRD and values arrays corresponding to the data representing for each row. And of course, for each row, you have the data in CRD corresponds to the non-zero coordinate in that row and also the non-zero value. So, put this in mind. The main intuition for how a compiler like DISTAL works, I think this is if you want to remember one thing from the talk, it's probably this slide. And we exploit this intuition that the partitions you need to make of sparse tensors have static structure, meaning the relationships between all these arrays have a very static shape. So for CSR, it's defined in a certain way. But then the actual shapes that these partitions have is very data dependent. It depends on how the actual non-zero pattern of it was. So here's that CSR matrix. I've chopped it up into pieces. So I've chopped it up into rows. And kind of for each row, I've colored all the data you need if you want to access the data for that row. And so when I say that these partitions have a static structure, I can write down a little program that represents the pieces of each array I need given a partition of one of these arrays. So for example, if I need to describe the pieces I need of CRD given a partition of the pos array, well, I can do that by kind of taking all of the entries of the pos array, unioning those ranges they have together, and I'd get out the corresponding pieces I need of the CRD array. So I can write down a little closed form program that represents this, but of course, I need the actual data at runtime to produce this thing. Another example is suppose I have a vector, I'm doing something like an SPMV, where I need to locate from CRD into this vector. Given a partition of CRD, well, I take all of the coordinates in CRD and I union all those together, and that would be the corresponding pieces of data I need in this vector class. So right, we have a static structure, but a very dynamic shape of these things. So our compiler exploits this intuition by basically defining a series of partitioning operators that are used to construct these structured partitions of these arrays. We have things like tilings, so you can take an array and break it up into equal pieces. This is not necessarily involving anything dynamic. Then we have these other operators that actually called dependent partitioning operators that perform some dynamic behavior here. So these arrays basically these operators basically relate partitionings between two different arrays. So I have an image is defined that if I have like that pos-like array before that holds ranges into another array, an image is going to follow this indirection through. Right? If I have a partition of this source array, I get the corresponding, I partition it by following each range inside there and partitioning the destination in the same corresponding way as these ranges describe. And interestingly here, I sort of statically write down that here's my image, and then the actual value of it depends on what the sparse matrix data actually holds. And we're going to use a dynamic analysis when actually doing this thing in the compiler. We also have this kind of an inversion of the same image called the pre-image. We're given a partition of this array of coordinates or something. We can find the corresponding ranges that we would need to look at if we want to go the other way. So the way our compiler uses these partitioning operators is kind of through a format interface, which is the same way that many tensor compilers like Taco work today. So in compilers like Taco, there exists one compiler algorithm, and that compiler algorithm interacts with the different data formats through an abstract interface that the interface is defined kind of for each format that you might have in the program. So you have standard API calls that you maybe would say, the compiler is like, how do I get the range of this loop? Or how do I get a particular coordinate from my sparse matrix? And the format interface will return to you snippets of code that say, for the sparse format, here's how you do it. We extend this format, we extend this API with talking about partitioning operations, where individual formats will describe, say, hey, I made up of a few arrays. You should use a tiling to partition this array that I have, or you should use an image to partition this other array in this format. And so then we have one compiler algorithm that uses this API and dispatches to the right partitioning operators for each kind of format. To give you a very high-level idea of how this works, the compiler generates code by walking through the different levels in your sparse tensor and then outputting the corresponding code. So if you have something like an SPMV, the compiler generates code by asking each of the levels in the sparse tensor, how should they be partitioned, and then dispatches some code that actually runs on each individual GPU or CPU in your system, generated through a standard lowering procedure, something like Taco knows how to do. Okay. So I've given you a very high-level idea of this DISTAL compiler. So how do we actually use it when writing this Legate library? So we completed the initial version of this library around 12 weeks, which I think is really fast for what I pitched to you, this distributed multi-GPU sparse library. And the reason why we were able to do so fast is because instead of, for every new operation, writing down a ton of CUDA code and corresponding partitioning logic and all the communication, we just write down a very compact schedule inside the DISTAL compiler. DISTAL goes and generates a ton of low-level code that we then lift into our corresponding API. And we were able to generate almost 50% of this library, 50% of the C++ of CUDA in the library, and around 10% of all the Python completely automatically. And the real important thing is that this is all the hard stuff in the library. Kind of the performance core set of kernels is all automatically generated, so you don't have to go spend time debugging them or manually optimizing them. It was kind of all done by this automatic process. So we could go and spend our time doing much more interesting things, like developing those cool applications I showed you at the beginning, or really stressing this composability aspect of the libraries. So one thing that was a bit unsatisfying to me that I think is definitely something you can do in the future is that I really like to see, rather than using DISTAL as a head of compiler, we would like to use this compiler technology just in time, kind of keep it all inside the loop. And I think that we really need to improve our auto-scheduling frameworks to make this happen. I think, we've heard a bunch of talks. We've heard a talk today about auto-scheduling, and we'll hear some more talks by Willow about it. But I think that we yet don't quite have fast and reliable auto-scheduling, where fast meaning like in a millisecond or two come up with the schedule, and then reliable means I can kind of always trust it to do something reasonable. I think we're not quite there yet, and so for now we still need a human to come up with this schedule in our libraries, and we'll probably be stuck using them as ahead of time things for a while. But there's still a pretty big win in the productivity. Yeah, so Willow's going to talk about this stuff, but I think we made a ton of progress, especially now we're really good at getting the asymptotics of these sparse tensor contractions right. And once we have this, now we can then get some of these heuristics about when to parallelize things the right way, what tile size to use, and then we could actually have this compiler technology be just in time rather than ahead of time. So with that, I'm going to stop. I guess I thought that would be mostly a 15-minute talk, and so we were 20 minutes, so I went a bit slower. But I was telling you today that you can go download Legate Sparse. The engineers work hard on this stuff, so I'm told that this con install actually gives you a multi-GPU, multi-node version of this package. So you can just con install and get the distributed version of the code right away. And I want to say that I think Legate Sparse has been a result of a ton of progress that we, the Sparse compilation community, have been making over the last 10 years. This stuff has been going on for a while, and the compilers we built have enabled really rapid development of kind of difficult software. And so I think that that's a really big win for us in this room. So with that, I'll stop, and I guess we'll take questions during the panel. So thank you, everyone.